First, thank you for giving me the opportunity to have this talk, to present my work. And congratulations for the impressive work of this conference. I am Luciano Mazza, and today I present the work that I did in collaboration with Polytechnic di Bari, University of Messina, and Chinese Academy of Sciences. The work is named Unconventional Computing using spintronic oscillators. And indeed, today I present you one way to implement the analog multiplication using spintronic oscillators. And then we apply this analog multiplication. We use this technology to implement the convolution, and we apply the convolution in artificial intelligence, in neural networks. And I want to start this talk with a brief introduction about how artificial intelligence is getting through our lives. In particular, the theme I want to start with is the self-driving cars that now are getting more and more popular, and the forecast is that they will be the normality in more or less 30 years. And the image on the right says more or less, shows more or less how an automatic vehicle perceives the world, and it needs to understand what's happening in the surroundings at every moment. For this reason, there is the need for high, efficient, and very fast neural networks. And this is the reason why major industries of electronic components are investigating unconventional and neuromorphic, which are analog solutions to implement neural networks. And in particular, the image recognition, as the example here, are based, the vast majority of them are based on convolutional neural networks. And this is the focus of my talk. And the convolution operation is defined as the accumulation of multiplications. And to implement this in an analog, but also in a software way, the easy part is definitely the sum, the accumulation. And the complex one is the multiplication. And here we present a way to implement the multiplication using the property of parabolas. In particular, it's easy to show that we can multiply any two numbers, in this case f and g, just making three measures out of parabolic phenomena. And then we need just to sum them and to do a very quick mathematical conditioning. So we can obtain the analog multiplication from any starting parabola. And the question is, which parabola to use here? For this reason, we investigated spintronic diodes. Spintronic diodes are spintronic oscillators where the input has a continuous part and an alternated part. And in particular, the alternated current that is inputted has a frequency very close to the self-oscillating frequency, so that the devices locks to the external signal. And this process is named injection locking. And we can see that when the injection locking happens, we can tune the DC component, and we will obtain the output continuous voltage that has a peculiar parabolic shape. This curve states more or less how much the self-oscillation frequency is close to the external one. For this has this big peak here, this parabolic shape, and we name this degree of rectification. The very interesting part is that we are dealing here with continuous components. So we are giving a continuous input and we are observing a continuous output. And this makes very easy to deal with this device. And also the time to gather each one of these points is less than 15 nanoseconds. So we are talking about a very fast device, and there is no need for magnetic field. So we want to corroborate this experimental data that was obtained by Fang in 2016, and we corroborated it with micromagnetic analysis. And also here we observe that there is the parabolic peak is very close to the data that we collected. So we took the parabolic data also from the experimental device, and we applied both of these to implement the analog multiplication. We can see here a plot of the door multiplication versus the ideal multiplication. And ideally, these black dots would be over the red line, which is the bisector of this first quadrant. But this is not true because of there is a slight error, and this is due to the fact that we are not dealing with a perfect parabola, and we are not dealing, with a perfect second order curve. And we gathered both of this plot for both of the cases, and we can see that for the experimental data, this is even more noticeable. So we have the analog multiplication, and we can implement the analog convolution. Here you can see an example of the image of a snail that has been convoluted by a blurring filter. And you can see here the ideal convolution obtained, the simulation-based dot convolution, that is the one obtained with the curve in the top left, and the experimental-based dot convolution, which is the one obtained with the curve here in the top, in the middle. There are some differences between these three images, and this is due to the error I was showing before. But in particular, what we want to state here is that these differences do not influence the recognition process of a convolutional neural network. And to do this, we apply this convolution in an exemplary neural network that solves the MNIST recognition problem. The MNIST database has handwritten digits, and we use these as input to our very small network that is based on a convolutional layer and a fully connected layer mainly. And what we can see is that in the ideal case, we got a more or less 98.6% of accuracy. And when we apply the DOR technology in the convolutional layer, we got a drop of about 2 percentage points. We got down to 96.8%. But then just making a fine tuning, a really quick training of the weights, we got back to 98.4. So these are the accuracies that we obtain without the DOR, so the ideal case, and with DOR. And here there are two examples of recognition of two numbers. In particular, in the histogram here that you see, the y-axis represents how much the network is sure that the number belongs to the class here in the x-axis. Here we are showing the case with the DOR, so the red one, and without the DOR, the blue one. And in the first case, both networks agree that this is a 1, as it's shown here. And the second case that I'm showing here, just for curiosity, because it was interesting to me, is one of the limit case, one of the case that makes a difference between the two networks, one of the 0.17%, which is this 2 that has been correctly recognized by the ideal case, the case without the DOR, and this recognized as a 7 in the other case, using the DOR. Without the DOR was correctly, and with the DOR is recognized as a 7. But this is one case that I also would be able to guess wrongly. So wrapping up, we defined a method that allows for fast, low size, and ultra low power hardware implementation of the convolution using spintronic devices. We corroborated that the experimental data with micromagnetic analysis, and we applied successfully this method in a convolutional neural network. So thank you for the attention, and we published a work about this. The name is Computing with Injection Lock Spintronic Diodes. You can find the link here. And I want to thank you also, all the co-authors of this work. And for everything, there's a question session now, but for anything, you can send me a mail. You can contact me through this mail address.
Thank you, Luciano. It was wonderful. Audience, time for your questions. So if you have any questions, and I'm sure you do, then click the raise hand button and we can unmute you, and then you can ask a question yourself. Meanwhile, my question is, so now you do convolution. Convolution is multiplication and addition, which are the two fundamental tasks of information devices anyway. So that is something that people know now very well how to build, at least I think, on GPUs, tensor cores, and all this stuff that is optimized to do specifically this task. So why use the spintronic devices instead?
Yes, mainly the main answer is that GPU are optimized to do the convolution, but still is a very complex task. If we are able to find a device that is able to just do this particular task and to do in an extremely fast, to do in a very with a very high efficiency, we would cut all the energetic problems that we have at the moment, and we will remove the bottleneck that is present, that is due to this operation. The bottleneck of neural network at this moment is basically due to the multiplication, and in the image recognition side is because of the convolution. So the idea is to build a coprocessor or a device that is in addition, we put it in addition to the GPU, and it just does this this operation with an extremely high velocity and efficiency.
Okay, then looking forward to the next papers on that.